This is going to be a brief tutorial on polar regions or polar rectangles, focusing both on if you're handed a polar region, can you draw it, and also if you see a certain type of region, can you express it in polar coordinates. We're going to compare everything that we're doing here to Cartesian regions or Cartesian rectangles, which you've done a billion times. What I think of as a rectangle, in a very general sense, is any interval cross interval. Anytime you have an interval and you're crossing with an interval, bam, that's a rectangle. Whether you're in Cartesian coordinates, polar coordinates, it doesn't matter, spherical coordinates. So here's some friendly axes with an x and a y. And let's say I have two intervals. You know how this goes. The 1, 5 is meant to go with the x. The 0, 3 is meant to represent a set of y values. And so if you were to mark these axes somehow, we can just make 1 unit equal 1 box. And then you would mark out the two intervals on the two axes. So there's 1 and 5, and here's 0 and 3. And so those tell you the edges of the rectangle, and you shade in. And notice how the different combinations of these endpoints become the corners of the rectangle, right? So 1, 0, 1, 3, 5, 0, 5, 3. You can find all of those there. As a second example, here's -8, -2 crossed with 1, 6. The only thing that's truly different about this example are the parentheses instead of the brackets, right? Now this starts the same way. Notice how I've already done part of this. We have -8 and -2 marked. We have 1 and 6 marked. And I have two dotted lines here. And the reason I'm using dotted lines is because I actually don't want these edges in my shaded set. I need to represent that those edges are missing. There's going to be a third dotted edge here, and this edge is going to be solid. And I mean, think about it this way. Is the point -5, +1 in the set? Yes, because -5 is inside of here, and +1 is inside of here. Is -5, +6 in the set? No. -5 is in here, but +6 is not in here. And so that's why you use the dotted edges. And of course, we need to shade this guy in. So on to polar regions, or polar rectangles if you like. Again, interval cross interval. So here's an example. Draw this, okay? It's just interval cross interval. Now, the first interval always goes with r, and the second one with theta. And I'm going to label these axes. The thetas, I think you know, it's just from 0 to 2 pi, so I'll spare you that. But I'm going to choose each little tick mark is going to represent 1 unit. And so this goes the same way. On the r-axis, I'm going to color in between 1 and 2. And now theta sweeps out from 0 to pi over 2. This is 0, and this is pi over 2. And so I start at the 0 here, and I'm sweeping out with this edge and sweeping out with that edge. And then on this positive axis, which is also representing r, I have colored in from 1 to 2. And that guy gets shaded in. All solid edges. Why? Because it's all square brackets. Here's a second example. R is between 0 and 2. We're not including 2. Theta is between pi and 2 pi. So in this case, I relabel my axis, and I'm going to mark from 0 to 2 with r. So notice how I have, like with my interval, when I color intervals on the number line, I'm using that notation. I have a solid dot here at the 0 and an open bubble at the 2 to remind myself about this strict inequality. I also looked ahead and I saw this theta. That's why I drew the r's going this way, because I knew that theta started at pi. So I actually drew that going off to the left. Now, theta goes from pi to 2 pi. So it starts pointing here, and it sweeps and sweeps and sweeps and sweeps. So you're going to take this open bubble, and you're going to sweep it across that pi. And you're going to take this solid dot, and you're going to sweep it. Except this time that's kind of stupid because it doesn't move, right? It just like rotates. So you're not actually going to draw a fourth edge. So even though this thing has 3 edges, it totally counts as a polar rectangle. Semicircles are polar rectangles. They can be represented as interval cross interval. And here are my 4 vertices for this polar rectangle. I have 0, pi and 0, 2 pi are actually in the same place. Here's 2, pi, and there's 2 comma 2 pi. Here's my last example. Here's an annulus, a little donut shape, and I have a solid edge on the inside and a dotted edge on the outside. Could we represent this annulus or washer as a polar rectangle? Is it even a polar rectangle? And yes, absolutely it is. And the secret is to snip it. Now, I am totally generic and I do the same thing every time predictably, so I always snip it theta equals 0. You could be a total freak and you could snip it anywhere you want. I really don't care, but I'm going to snip at theta equals 0. Now, let's assume that my r's are the same as they were in the other examples, okay? So that means that my r's are starting at 3 and ending at 6, right? So my interval for r is 3 to 6. What are my thetas? Now I snipped here, which means I start at 0, but this guy goes all the way around. And so that interval is 0 to 2 pi. Okay, so I'm done with this problem. Now these r's here are pretty non-negotiable. You have to have less than or equal to here. You have to have strictly less than here. But what's going on here? You may wonder why I have less than or equal to on both times. You may be saying, well, don't those 2 lines overlap? Yeah, they do. And I guess I could change out one of these for a strict inequality, but you know what? The reality is you could do that and I could do it my way and we would both be right. And the reality is there are millions, infinitely many intervals that actually work for this. You could, like I said, you could be a total freak and you could snip it here and then your interval would be pi over 2 to 5 pi over 2. You could start at negative pi and go to pi. You could start at 0 and sweep to 1000 pi, which is actually 500 loops around. But it's still going to color in the same region. So this would be a pretty silly interval, but you would be totally correct in saying that. So there are infinitely many correct expressions of this annulus as a polar rectangle.